Okay, so today we're going to be talking about the analysis of statically indeterminate trusses. So remember that up to now we've been talking about beams and how we can use the flexibility method or the matrix methods to calculate them. In this part, we're going to be showing how exactly the same process can be repeated for trusses. So before we start, I wouldn't mind having a chat about statically indeterminate trusses. Firstly, I think everyone would be happy to say that this is a statically determinate beam. But what happens if, so that's got a load coming down there. But what happens if I turn that into a pin? So that's this side is pin and this side is roller, and this side is pin and pin. So this one is statically determinate, but this one here is statically indeterminate because here you've got three reactions: one vertical, one horizontal, one vertical. And then here you've got one vertical, one horizontal, one vertical, and another one horizontal. So you've got four. So here, this one becomes statically indeterminate. And now the same thing applies to trusses. For example, you could have a truss system like that one there. So each one of these is a pin, okay, and then one of them is pin and this one here is roller, so that one is statically determinate. Now the thing about trusses is that as long as you keep on adding another triangle, then the structure remains statically determinate. So for example, that here you've got three triangles. Okay, so let me add on another triangle, okay, like there, and then let me add on another two, and then let me add on another triangle here, and I can go on for as long as I want. And this one here, and put that on the roller there. So same as this one here, and this one is still statically determinate. Okay, so this is statically determinate and this is statically determinate, and that's because trusses, that's because triangles are a sort of a stable shape. So let's have a look at this one here. So if I said that one, so again, so note I've not stuck any loads on. I could if I wanted to. Not that it matters what loads you put on, it's still statically determinate. So this one here is statically determinate. So that's pin and that's roller. Okay, so the support conditions means that it's statically determinate, and the fact the number of interior members is just 3 in the situated position in the triangle still makes it statically determinate. If I added another one on here, that is still statically determinate. So it's statically determinate in terms of the support or boundary conditions. This one became indeterminate because it was pin-pin. This one is still pin-roller, so it's still statically determinate. It's made up of one set of triangles and another set of triangles, and so it's still called statically determinate. But what happens if I took exactly the same structure? So let me draw it out again, and then with one member there, again the same support conditions. What happens if I then put another cross member along here? So if I had another cross member, so it would go like that, going to there, this one suddenly becomes statically indeterminate by 1 because of the extra member. So sometimes, these might be two flat plates of steel, so they could be rubbing between each other. Just to be really clear, or sometimes they can just be 2 bits of string. It's actually tension only bracing, so sometimes it could be just 2 bits of string or wire, and suddenly you've got a statically indeterminate problem. So sometimes it's shown by that, and it's drawn by that to indicate that that's not another pin, okay? Because if we had something like that with a pin there, and then we had another triangle here. Remember what I said about building up the triangles means that it's statically determinate. Put another, let's get rid of that one there. Put another one here, okay? So this would be called a node, and then put another one down there. So we've got 1, 2, 3, 4 triangles. This would be statically determinate, okay? So just watch out. So this could be another, there's a crossing between the two here, and it doesn't meet at a node there, like you can see from that case there. And if you wanted to stick some loads on, feel free just to stick some loads on there, okay? So method of sections, method of joints would enable you to work out the forces in each of these members here. Method of sections, method of joints would enable you to work it out for here. Method of sections, method of joints is fine for that one. Method of sections, method of joints is fine for that one there, but it's not fine for this one here, okay? And to solve this statically indeterminate problem, we are going to need to use the flexibility method. So exactly like we have with the beams, where we removed a support, in this case, or with the beam here, we turned it into a pin. In this case here, in order to solve the statically indeterminate problem, we're going to be removing one member that would then restore it to a statical determinate structure, and then we'll be applying a tension or compression force back into the structure to take that into account, and then putting that into a matrix. But that's jumping ahead. So here I just want to establish that a structure can be statically indeterminate because of its supports. If I put that as a roller, then again, if I put that as a pin, then again it's statically indeterminate. But if the supports make it statically determinate, then this one here would become statically indeterminate because of the extra member that has been put across as a result of the two diagonal members crossing each other, okay? And for this type of structure, we would be using the flexibility method. Okay, so let's have a look at the notes. In this discussion, we restrict ourselves to 2D trusses loaded in their plane. The loads are applied only at the joints. Member connections are concentric and all joints are perfect hinges. The truss does not undergo significant geometrical changes, unlike a cable. Unlike under such an assumption, normal forces exist in members. Real trusses satisfy these conditions only approximately. Nevertheless, the member forces obtained using these assumptions are sufficiently accurate for practical purposes. So, starting with a basic stable triangular configuration. So here is a stable triangle, which you can see there, consisting of 2 members and 3 nodes. We've got 6 unknown degrees of freedom to determine 4 external reactions and an axial force in each member. At the same time, we can isolate each node and write 2 equilibrium equations for the free body, and thus we've got 6 equations, and then we've got this formula, okay, which you can apply if you like to try to find out if the structure is statically determinate or statically indeterminate. I actually don't like using the formula. I just like looking at the structure and just working it out for myself in my head, because sometimes the formulas, because sometimes you get structures which sort of trick the formula by having too many releases in one member, for example, another release here. It might be okay with the formula, but that then becomes a mechanism. Okay, so you can use the formula fine, but it's quite good to know the limitations of using the formula, and it's even better possibly just to be able to look at the structure and see if it's built up by triangles, and then be able to decide for yourself without the use of the formula if it's statically determinate or not. So the basic configuration shown in figure 1. So figure 1 is not this case here where you've got that there. Figure 1 is where that one there is missing. Okay. And we've got some loads being applied. So the basic configuration shown in figure 1 can be used as the building block for expanding the truss. As shown in figure 2, acting one more triangular portion, as I've said, preserves the truss stability, i.e. it doesn't become a mechanism, and increases the number of members by 2, but at the same time introduces a node with 2 additional equilibrium conditions. We now have 4 members, 4 nodes, and 8 force and 8 unknowns to determine, an axial force in each member. So that's the formula. Number of members, number of releases, minus 2 times the joints. So use that equation if you really want to, but try and understand what's happening in terms of the building blocks of the triangular portion. So formula can be used to study statically indeterminate trusses, and if it's this one here, then so it talks about sufficient condition as the truss may still be unstable, and that's really why I prefer to look at the truss and decide for myself if it's been built up with triangular sections, because the formula can lead to an incorrect observation. And then this one here, if it's greater than 0, then it provides a necessary condition for statical indeterminacy. However, it is not a sufficient condition, as the truss may still be unstable. Again, why I'm not really too keen on using the formula, because you can make it statically indeterminate, but just by adding something within one member, suddenly the truss would collapse. Okay. So that's the basis of the formula. So I think I hopefully have explained why this structure here is statically indeterminate. So so for this statically indeterminate problem, we want to be able to work out, we wish to be able to work out the forces in this statical indeterminate solution. So the first thing to do is to introduce a release. So we introduce a release almost exactly like we did in this case here. So we introduced a release here, so that the bending moment then became like that and like that. Okay, so that's very much similar to what we're doing here. And the way that we introduce the release is, say, by putting a cut here. So if you want to come along with a hacksaw and you wanted to make a cut, then, which is effectively the same as removing which is effectively the same as removing that member, then we get back to a statically determinate problem. Okay, so first step here is, like before, is to take the introduce a release. Okay, so we're going to be making the release. It can either be that member, or it can either be this member, or it can be this member here. It doesn't really matter for all intensive purposes which is the member that we're going to be applying the release to. So let's say that we put the release here, okay, and remember, you know, these are all pinned. Okay. So along here we've got that member there, another join there, and then put that on the roller. Okay, so you apply the force P to this case here. So what's going to happen? You apply a force P here. You're going to know that that force is going to be downwards by P. That one's going to be upwards by P, and you know that there's going to be no horizontal force. Sorry, you know that this one here must be in equilibrium with that one there, since that one is on a roller. Okay. Now, the next step, so use method of sections, method of joints to work out all the forces in this truss. So the next step is to take exactly the same truss that we've got from before, with the diagonal member, and then to say that we've made our cut, and now I'm going to be putting the effect of that as two forces, okay, at the end of each member, and I'm going to be calling this my 1 bar. Okay, so 1 bar. So maybe I'll get rid of the bar. Maybe I'll get rid of the bar here. Right, so we've got this case here, and then we've got the identical case. So this case has the P. This one here doesn't have the P being applied, but we've got this case here where we can solve everything except knowing the effect of the diagonal member. And in this case here, we're adding back the effect of the diagonal member by applying 1 here, which we can scale upwards. So last time we used the factor x to scale it upwards, such that, so before the condition was we wanted to make sure that at the end it didn't deviate off the 180 degrees, or there wasn't a kink as you would get there in terms of the deflected shape. And in this case here, we want to make sure that the joint doesn't move. So exactly the same as before, by adding the two together, we should be able to calculate the forces in the diagonal members. Okay. So tomorrow I'll be talking about that in more detail.